Guys, we are still in chapter 6. We are in multiple phase mass balancing. We're going to talk about the solubility coefficient of a gas. It's defined by the amount of cubic centimeters of that gas that dissolves in 1 cubic centimeter of a solvent under a partial pressure of 1 atmosphere. The solubility coefficient of CO2 in water at 20 Celsius is this one. First of all, they tell you to calculate the Henry constant for this, and then they tell you in letter B, use this Henry constant to calculate the amount of grams of CO2 that are stored in this 12-ounce bottle, and then with these grams just turn them to moles and then to volume by ideal gas. They tell you what is the volume. So let's do it. It's kind of easy. It seems large, but it's not that large or that time required. Let's calculate letter A. They tell you by definition Henry law, it's the pressure by the molar fraction. So at 20 Celsius we have 1 cubic centimeter of water. I'm going to turn it, the density, it's 1 gram of water. And not only that, I'm going to turn it to moles by molecular weight, which is 1 gram of water divided by 18 grams per gram mole. So I got this number, 5 gram mole of water. Good, I have moles. What I want to do is to first find the mole fraction of CO2 and then put it here, put the pressure here, and I got Henry constant. So let me work first for X CO2. For X CO2 I need the moles of CO2 divided by the total moles. Total moles, we're going to add them later, but we now need to find moles of CO2. So a specific gravity of CO2 it's 0.09. This is referenced to centimeters. Is cubic centimeters per gram mole. So it's cubic centimeters per gram mole. I found out in internet at this temperature, of course. Then with the standard volume, I'm going to change it to see how much does that occupy. So it's 0.09 cubic centimeters CO2 divided by the gram mole. And 1 gram mole I know occupies 0.4 times to the minus 3 cubic centimeters. So I'm going to get, this is not gram mole, this is only cubic centimeters. I'm going to get the amount of moles of CO2, which is 4.02 times 10 to the minus 6 gram moles of CO2. So I got this, and total, let's calculate it. And total is only NCO2 plus these moles, which is moles of water. So I don't know why I'm writing this, because I know it's nothing, so I could just throw it away, but just put it. You can do this operation and you will get this. So the total moles, you can say that the total moles is approximately moles of water. So let's go find XCO2, which is NCO2 divided by N total, 4.01 times 10 to the minus 6 divided by N total, which is this number. And XCO2, how much is it? Got 7.27 times 10 to the minus 5 XCO2. So that's interesting value. It's a little bit, it's almost nothing. So how do we turn this to Henry law? Henry law is essentially the pressure we are using divided by the mole fraction of CO2. What's the pressure? I think it's 1 atmosphere. If I not remember, okay, let me check. Yeah, 1 atmosphere. And my mole fraction is this one. So doing this I got 13,755 atmospheres per mole fraction. That's letter A. Now, letter B. How many grams of CO2 can be dissolved in this amount of volume at 20 Celsius if the gas above the, okay, they give you this pressure. And the liquid or the soda we can suppose to have water properties. So essentially, essentially we are asked to calculate the amount of volume, which is, or well, the amount of mass. So what I'm going to do is first, I don't like working with gauge pressure, so the atmospheric plus the gauge should give me the absolute. So it's 1 atmospheric, 2.5 gauge, so we are speaking about 3.5 atmospheres in this condition. So the volume, I know 12 ounces of liquid, it's equal to, and without doing this, guys, by experience, probably you've seen in the supermarket or whatever, you have seen this typical value of milliliters, or in this case it's liter, but you should know that 12 ounces, it's about 355 milliliters, because of the cans. All the cans, which are almost international size, have this amount, either 12 ounces in an English system or 355 milliliters in the international system. So X CO2 times, let's apply Henry law, let's apply it. You know that it's the mole fraction of CO2 times the H, we just calculated, so the Henry's constant, by partial pressure. So let's see how much do we have here. This is 3.5 atmospheres divided by this 13,755 atmospheres per mole fraction. X CO2 shall be 2.58 times 10 to the minus 4 mole of CO2 per mole of mixture. So I got this. Now let's find how much moles do we have in that volume. So volume was 0.355 liters. How many moles or let's go first find with density. I know it's because it's water, or we are modeling this at water. It's 3.55 kilograms of liquid. Now the amount of moles equals the amount of mass divided by the, ignore this point, by the amount of mass divided by the molecular weight. So 0.355 kilograms of water times, or divided by, the amount of kilograms of water per 1 kilomole of water, and you will get this into 0.0197 kilomole. Let me change that to grammole, 1972 grammole. So that's the amount we have in that volume of water only, or soda. Now the moles, I told you it's 19.72 gramoles of water or soda. Now how do we account for CO2 moles? X CO2 times the total moles should give me that. So X CO2 I just calculated is 2.58 times 10 to the, how much is that? 4 times the amount of mole, which is 19.72 grammole of mixture. This gives me the moles of CO2. Moles of CO2 will be something about 0.005 gramoles of CO2, which we're going to change. How do we get mass of CO2? Just by multiplying the molecular weight. How much is molecular weight? It's 44 grams per grammole. So doing this operation, I got 22 grams of CO2, which is the question. How much grams can I have there? 0.22 grams. It's not that much, but I assure you guys that when you don't have those 0.22 grams of CO2, you wouldn't be able to feel the refreshing or the bubbling effect, the sparkling effect of the soda. So let's see what volume will that dissolved CO2 occupy if it were released from solution at the body temperature. So that's curious. Probably they're supposing what will happen if you drink it. You are here, you drink it. And of course, temperature and pressures going to change. They want to know how much volume is going to occupy in your little belly, tummy. Let's do it. It's very easy. We're going to use ideal gas for this. Okay, so it's the amount of moles and CO2 times Vs and S. This is standard conditions. So this is 1 atmosphere, it goes away. And CO2 it was 5.12. No waste. 00 is this value here. 0.005 grams of CO2 divided by how much volume do we occupy? 22.4 liters per gram. And the temperature, it's 37, the one of the body, times 33. And yeah, 273 is the standard. So let me calculate that for you guys. 0.005 times 22.4 times 37 plus 10, okay, divided by 273. I got 0.12. 7 liters. So you can either let it like that or use it in milliliters, will be 170 milliliters. And that's the amount, guys, that you're going to have displaced in your body. So it's almost nothing. It's about 0.1 liters. So you compare it to a Tetra Pak brick of milk, it's only 10% of that. If you eat or you drink a complete soda. So imagine you had 10 sodas, you will have a displaced volume of almost 1 liter, that is actually a lot. Yeah, essentially is the problem. The only thing where you kind of tricky is this one, in which you calculate the amount of moles of CO2, but after that I think it's easy. Total amount of moles, it's obvious that it's the amount of CO2 plus the amount of water. The amount of CO2 actually is so small that you can say it does not exist, so you can assume this. If I were your teacher, I wouldn't be mad. And yeah, the mole fraction by definition is moles of CO2 by moles of the total mixture. The Henry constant was another one that was kind of tricky. You know the pressure? Yes. You know the concentration? Yes. So you got your Henry constant. Because this constant is to be supposed that is linear. So if you have one value, you will get another value. You give this value, it will respect this value, etc. Then we just calculated volume. This is just mass balancing. How much volume, then how much moles, and how much moles relating, and we got finally to ideal gas here. Solve for that and we find out the total volume. So that's everything, guys. See you in the next video.